begin our evening session. Today we have another special guest. It's Ivan Vulic from Cambridge and also Poly AI. So he's working in the university and also in industry. His Poly AI is a startup which is targeted at creating conversational intelligence applications. Am I right?
Yeah.
Okay, so today Ivan will tell us about data-driven dialogue state tracking using specialized word embeddings, and I hope his experience will be useful for all of us. So let's greet our speaker and begin.
Many thanks for the introduction. So I'll try to cover some of the work that we actually did in the last 2 or 3 years, mostly at the university, but we kind of continued on this line of research at company Poly AI that I will advertise a bit. You can also question me about it after the talk. So the talk will focus on one part of the entire pipeline of conversation systems, which is language understanding and dialogue state tracking. So I'll mostly talk about work that we did with multiple people. Okay, you don't see any names here, but so 3 people from this picture. So Nikola Mrčić, Peihao Su, and Sung-Xian Wen, actually they started the Poly AI company. They are PhD graduates from Steve Young's group. I don't know, Steve Young is a pretty famous person in dialogue, and yeah, he had companies sold to Google, Microsoft, and Apple, and he was behind the purchase of Vocal IQ that actually became Cambridge Siri team. And there are other people who are all over the world who actually worked on some of the ideas that I will talk about in this talk. So we will cover multiple topics here, and you might actually wonder at a certain point what this actually has to do with the dialogue itself, because so this talk will be more about the usefulness of natural language processing and semantics in dialogue applications. So we will have a large part of the talk will focus on semantic specialization. It will be basically fine-tuning word embeddings, word vectors that you probably all know about, like word-to-vec models, for particular language understanding applications like dialogue state tracking. And we will discuss a state-of-the-art model that does the specialization process, which is Attract-Repel. We'll see what it means. And then we will cover the first neural architecture that was published at ACL last year that actually can do end-to-end learning for dialogue state tracking, just based on the information that's coded in these word vectors, word embeddings. And we'll later show how we can use this neural belief tracking framework to actually bootstrap dialogue state tracking models for resource-low languages. And I will also discuss some recent improvements that we did on top of these basic models like Attract-Repel and a neural belief tracking model that can actually lead us to even better scores. So what is dialogue state tracking? Well, first we have to define like a high-level task-based conversation system. So I think you're aware that actually there are 2 main paradigms in designing conversational AI. So the first one are end-to-end open domain chit-chat style chatbots, which actually are nice as an idea because, yeah, by solving that problem, we might actually solve AI by having a system that can talk about life and universe and everything else as a human does and pass the Turing test and all that. But we haven't come to the stage where we can actually develop bots like that. So an alternative is to build what we call task-based dialogue systems, which actually target a specific task. That could be flight bookings, that could be hotel reservations, or restaurant search and booking. And what we actually can do here is optimize our conversational systems to be good at solving this particular task. So a pretty good example of this paradigm was recently with Google Duplex. So it's exactly that state of mind. So we can't have a bot that's good at everything, but what we can do is to gradually make a dialogue system that can solve particular tasks and train it on the domain-specific data if we can obtain that data, etc. So so one domain that we will actually stay in this talk is the domain of restaurant search and booking. And OK, so that's the main idea. So yeah, we won't talk about chit-chat style bots. We'll talk about these task-based systems that are actually modular or pipeline systems. So they usually contain these components here. So speech input comes in, and you have to do text to speech. You will get you have to do your ASR. You might actually have some errors in the conversion. And that's one of the problems, but that we won't be talking about that problem in this talk. So we'll just assume that we have text after speech was converted. And then the second component is spoken language understanding, which actually has to detect, it's like turn-level understanding of the user's intent in this particular turn. And in each turn, this goes into the dialogue state tracking module. And this module actually keeps track of users' current intents in the dialogue. So for task-based conversational systems, it's a probability distribution over all possible dialogue states, where you actually have a high belief that certain intents were expressed during the dialogue given the context of the current utterance, or you might actually have lower belief for some others. And this is actually more like a cross-turn understanding. It just keeps information across the whole dialogue in the loop, and it feeds that information to the dialogue manager, which has to, based on the information from dialogue state tracker, decide which system act to take next. And this system act is then generated as a natural language response of the system. And then you have speech-to-text module, which actually goes out, and that's the full pipeline. So we'll mostly focus on the part of spoken language understanding and dialogue state tracking in this talk. So so for task-based information systems, they need to have a task definition. So if you want to solve a restaurant search and booking, we actually have to define this task, and the task is defined by what we call domain ontology, which is actually that's a list of different slots and values that the user can utter in the conversation. So you can think of it, OK, if we want to book a restaurant, so slots are food area in the city, or like address, and etc. And the possible values for the slot food could be British, European, Georgian, Russian, African, etc. And for the price range, we also have slot values. We have values like cheap, expensive, inexpensive, etc. And this is like predefined. This is something that is pre-given in a task schema or task specification for each task. And so most systems, what they do, so like the rudimentary systems, they just do what is called like keyword spotting or keyword extraction. So what they can do is they just match what is actually given in the user utterance with what is actually in the ontology. So if somebody expressed, I want Chinese food, and you have a slot value pair in the ontology, it's pretty obvious that most likely the user uttered this intent that he wants Chinese food. And so this idea was actually used in what we call delexicalized models, because some of the problems are, the user can utter, user utterances can contain slot value pairs like food British and food English, etc. But one of the curses of machine learning approaches is that we don't have enough training data. So what do we do when we don't have enough training data? We basically want to generalize to rare phenomena, and we want to generalize to the fact that user expressed intent that he wants English food, although we haven't seen any training examples that contain word English. But we have other examples like food equals British, and he wanted German food, African food. And so the idea behind delexicalized dialogue state models is actually to replace all the actual occurrences of slot values in user utterances with like these generic tags, and then combine training of these generic tags with slot-specific training. Because if you replace, for example, if you have the utterance, I want Chinese food, and if you replace it with the generic tag value and slot, and you actually say, I want value slot, it doesn't matter if the user said, I want Chinese food, or I want northern part of town. It's, you actually have a similar structure in the utterance. So basically parts of the parameters between I want northern part of town, or I want Chinese food, I want Eritrean food, actually they are shared. And then you can further train the parameters for your specific slots. And what it brings to you is, yeah, some sort of transfer learning across slot values, because you can actually learn better parameters for unseen and rare phenomena in the data. And you can also generalize to these unseen slot values. And this also helps you to bootstrap dialogue systems to new domains, and also do like cross-domain learning. And this was all done in the work of Matt Henderson and Nicola Merksic that was published at ACL, where the idea was exactly that. Do Delexicalisation-based models with parameter, with slot-specific and slot and general pre-training of these slot-specific models. Yeah, so, but one of the problems with the lexicalization-based models is basically that they need an external resource to function well, because they need some sort of a detector of slot value pairs in the user utterance, and to do the replacement step. So, yeah, so for example, if the user says, I'm looking for an affordable restaurant, and you've never seen affordable, you can't do the replacement step. Although affordable is really similar to word inexpensive or cheap or modestly priced. So there are all these different rephrasings that could be expressed by user. And the problem with the lexicalization-based models is that they have to resort to what we call domain-specific semantic dictionaries that will give you all possible rephrasings for that domain. And okay, it might be quite easy to do that for the restaurant search and booking domain, but imagine if you go deeper and deeper, if you have really complex domains, it becomes infeasible to just have a human that will list all the possible rephrasings in the semantic dictionary. Yeah, so this is exactly what I just said. So the lexicalized features actually operate on exact matching. And if the user said cheaply priced, and we don't have cheaply priced in the dictionary, we can't detect that with the lexicalization-based models. And yeah, so one of the ideas that we had in our work is, okay, could we move past these semantic dictionaries that are task-specific and hard to actually compile for different domains, which reduces portability of the models. And of course, there were word embeddings to the rescue, because they give you, yeah, this semantic representation of words where you can actually measure similarity between different terms, and they offer you this generalizability that is not present in the lexicalization-based models. So if somebody says British food, and you've never seen that, but you know that British is close to English, there's a piece of information that we would like to exploit in the model. But yeah, there is one problem with word embeddings. So the way they are trained by word-to-vec models like skipgram and continuous bag of words, the problem is that they kind of conflate different word relations into like one single vector space, and what they usually reflect is just a broad conceptual association, or call it semantic relatedness between terms. So, and what often happens is that you have antonyms, like words with opposite meanings, as nearest neighbor in that semantic space. So we have a problem here. So the user, if the user says expensive, and one of the nearest neighbors of the word expensive in our semantic space is the word cheap, then we can't do the generalization well, because imagine if the user asks, okay, I want like a cheap pub in northern Oxford, and the system understands that, okay, yeah, that's an expensive restaurant in southern Cambridge, because these are like nearest neighbors of the words. And this is where the idea of what we call semantic specialization or word embeddings comes into place. And the idea is basically to make use, to leverage external knowledge that we have in external resources that were compiled over the years by different experts, human experts. So think about WordNet and BabelNet and, I don't know, Paraphrase Database, and there are like Thesauri, like Rockjet's Thesauri. So you don't have to pretend that we don't have these resources, at least for resource-rich languages. And one of the ideas is, yeah, we have this manually coded knowledge. Let's just use it. Let's combine the power of distributional training with word embeddings with this discrete knowledge that we have coded in the resources. And basically the idea is then to fine-tune, or maybe you've heard of the term retrofit, or distributional word vectors towards the knowledge from those resources to actually boost the vector space to reflect semantic similarity instead of this broad conceptual association. And if we are lucky, we will actually get true synonyms as nearest neighbors for words like expensive. So we will get rid of words like cheap in the neighborhood of the word expensive. And actually, all the rephrasings of the term east will be also linked to east after specialization. And you can see that this is not the case in the distributional vectors. So if somebody asks for a restaurant in the east, they might actually get a recommendation in the west. And so now I will kind of digress over the main path of dialogue and talk more about the specialization models a bit. So you can take this as a like NLP that works for conversational AI. So, okay, so I think I already mentioned the problem. In the perfect world, we would have something like this. So the user mentions that he wants English food in Eastern Cambridge, and our dialogue state tracker and like our language understanding module should understand that, okay, actually what we have in the ontology is food equals British, because British and English are synonyms, and that area should be East. So we should detect that slot value pair. But what usually happens because of the problems with distributional word vectors is that the language understanding module would think that we want an expensive Spanish restaurant and not an English one. And yeah, and the problem with dialogue is if you do mistakes like that, the whole thing just collapses, and the user satisfaction is just at ground zero, basically, and you basically failed in dialogue. So it's not like we have F1 score of detecting slot values of 80%. Yeah, what we have actually is a bad dialogue here. Okay, so this is also something that I already mentioned. So the idea is to use these external resources like BabelNet and Paraphrase Database to enrich the content in word embeddings that we have. And yeah, we can extract particular word relations. So for language understanding tasks, mostly synonyms and antonyms are useful because we want to pull synonyms closer together in the vector space and push antonyms far apart in the vector space. And they can come from all these different resources. And now I'll give just a short overview of several models that are out there. So the very first one was called retrofitting. And the idea is basically super simple. It's mostly like, it's most about minimizing this Euclidean distance between the original distributional vector and the specialized one while keeping still the content from the distributional space, because the main idea is, yeah, okay, if we don't have that information about word pairs in the lexicon, in the external resource, yeah, we should just stick with what we have in the distributional space because there is still some knowledge in the distributional space. So basically the first term is the regularization term, which says, okay, keep the specialized vector as close as possible to the distributional vector. And the second term is push them away to the vectors of their synonyms. So the first model, the retrofitting model of Faruqui et al., they just integrated synonyms in the procedure, and they cast it as more like a graph learning problem, but it's, yeah, it could be seen that way, but it's actually, it's super simple. Yeah, it's just about minimizing Euclidean distances in the vector space. And I think it could be solved by just doing like a solution of a system of linear equations. I think it's like 70 lines of code or something. So, but it already works quite decently, and it's only synonyms now. But what John Wieting and his colleagues do was actually a more sophisticated model that integrates the same type of constraints into the vector space. So still think about synonyms from WordNet, but the idea here is to do a sort of mini batch training with negative examples, where the idea is to take the synonymy pairs. Okay, maybe have, yeah, so here. Yes, is to take each synonym pair and then take negative examples, pretty much the same way as in word-to-vec models. But here we don't take random negative examples. We basically take the closest word to each word from the synonymy pair based on cosine distance, because we think that this one is semantically related. And then push two words from the synonymy pair by a margin closer to each other than to this closest other negative example. So here, if we detect that the English word fast is the closest one in the mini batch, the word affordable, and we actually have the link from WordNet that cheap and affordable are synonyms, and we have a similarity margin set to 0.6, for example, we're going to push cheap and affordable by margin 0.6 closer to each other than to the second best word in that particular mini batch. And yeah, so basically the formulation of this model is just standard max margin training where we do exactly this. And the trick is in choosing these negative examples. And the model does pretty much the same thing also for regularization as Faruqui et al.'s model. So we still want to preserve useful semantic information from the original distributional space. And we do it by keeping vectors of our original distributional space and specialized vectors as close as possible. So this objective is added to this one, and that's the final objective of the model. And finally, in the Attract-Repel model, you can see that model as sort of an extension of the Wieting and al.'s PARAGRAM model, but now we also have an additional term that does a similar thing to antonyms as we did before with synonyms. So we are trying to push antonyms away from each other in the vector space as much as possible. And we again do a per mini batch training, max margin training with negative examples, where negative examples are now the words that are farthest away from the pivot words from the antonymy pair. So again, in the example, if we have a link between cheap and expensive, so that's an antonymy link, and we find like the word boring, which is the furthest away from expensive that we could find in the mini batch, we actually push cheap and expensive as much as possible away from each other, so that they're actually by a margin further away than expensive and boring. So it's a pretty simple ideas, and it's an analogy with the synonymy thing from PARAGRAM. And then you can combine the synonymy objective and the antonymy objective and the distributional regularization into this final Attract-Repel model that actually works really well, as we might actually see. And yeah, so this is the high-level summary of the main idea. And it's still pretty much the best specialization model out there. Okay, so we talked about similarity specialization, and I think for many people, even in the NLP community, it's still not clear, like the relations between similarity and relatedness and conceptual association. But the fact is that for language understanding tasks like dialogue, relatedness is not enough, and actually it deteriorates, it decreases your performance. And what we want in the input vector space is to emphasize this relation of semantic similarity. And here we did some tests with Attract-Repel, and we used two pretty well-known data sets, which are used for evaluation of in distributional semantics in NLP, Simlex and WordSim. So WordSim measures broad conceptual relatedness, and Simlex is really tailored towards true semantic similarity. And the fact is really, okay, these two relations between words do not correlate well. And what we want to do is, for dialogue, is to specialize for similarity. And so, yeah, this is just a slide that shows you the improvements obtained with Attract-Repel. So the scores here on Simlex 999, I don't know if you're familiar with the data set. So it's actually 999 word pairs that were scored by humans to reflect the degree of similarity between words in each of those pairs. They contain nouns, verbs, and adjectives. And the numbers shown are system correlations, Spearman correlations with human scores. And inter-annotator agreement for the system is, I think, around 0.78 or 77. And that's the agreement between each annotator with the average of n-1 annotators. So that's how well humans do on the data set. And Attract-Repel is around 0.75, and we actually managed to even surpass the human performance on the data set. So now the system understands semantics better than the human. Well, okay, that's not the main message. And so what can we do with Attract-Repel and with those specialized vectors? I guess we won't come to that yet, so it's more NLP here. Okay, so we talked only about monolingual settings for now. So we can take our WordNet in English and do the specialization. But the interesting thing is that we also have cross-lingual repositories with synsets and with synonymy, antonymy relations. So we have BabelNet, which is like a collaborative effort that took years to build. And I think BabelNet is currently provided in 200 plus languages of the world. And so we can also inject these cross-lingual constraints into the vector space and also learn relationships between words in different languages. So we just pretend that the languages do not exist, and we just cram everything into one gigantic cross-lingual vector space. That's what we do in the field of cross-lingual word embedding learning as well. And yeah, the idea is to learn these shared cross-lingual vector spaces. And if you do this correctly, what you actually get is a pretty interesting result. So I think these lists are lists of nearest neighbors when we actually cram, for example, 3 Slavic languages in the semantic space with English. So if, words like rug or teppich in my own language. And so I think all these lists of words here in the nearest neighbor are actually very semantically similar to the given pivot word. And we'll come later to why this is potentially useful for cross-lingual, for bootstrapping of dialogue systems in other languages. And another message here is that cross-linguality actually helps, and that all types of constraints are useful for boosting the performance. So if we just plug in monolingual synonyms, it helps. If we also use antonyms, it helps even more. If we do the cross-lingual learning, it helps even more, and it boosts. So whatever we can get from the repositories, just put it in. It's better than your statistical distributional learning, because it was humans who actually handcrafted this mostly, and yeah, that's the main message. And another interesting thing is basically that this always seems to help when we do cross-lingual specialization, even for unrelated languages. Like if you do Irish Gaelic with English, or if you do like Farsi with Portuguese, it still kind of helps. And then we were actually thinking about this, why is this happening? And I think the main intuition is basically that other languages provide some sort of cross-lingual grounding for your source language, which can resolve the problem of polysemy and synonymy. So if you have 2 words in the source language translating or having synonymy links to the same word in the target language, that actually also means that these 2 words in the source language are synonyms. So by transitivity, you can actually get extra information plugged into the vector space. And this way, we created 50-something bilingual vector spaces that are hosted online, and NLP people kind of like that, so they keep on using it. Okay, I guess this is already said, so it's, yeah, more about. And yeah, so this is exactly what I said. So this is BabelNet, and these are some numbers from BabelNet. And given the amount of content that we have there, I think people shouldn't really pretend that such resources do not exist and just try to do end-to-end statistical learning without any additional information. So you might have heard a lot about reinforcement learning during the summer school, and if you want to talk to me about not believing in reinforcement learning after this, we can talk about that. Yeah, but so the idea is, yeah, let's use knowledge that we have already along with the power of statistical modeling, which will finally get us back to dialogue. So it was all about vectors and embeddings until now, and about resources and specialization. And so the next part of the talk will focus on how to use these vectors for dialogue state tracking, how to boost language understanding. And yeah, so going back to the lexicalization-based models, so one of the problems with those models is they needed those semantic dictionaries. But given what we were discussing now with like nearest neighbors lists and all that, so you kind of already see the link. And basically, you can maybe use word embeddings to create those semantic dictionaries, or you can use them some other way. So the very first idea that we tried, it worked decently, but there are other things that work better, is basically to build semantic dictionaries by just taking synonymy lists from the specialized vector space, and we already got some boosts over the lexicalization-based models. But what I'm going to talk about more is the neural belief tracker model from Merkshich et al., which is this model/framework that can consume word embeddings and pretty much nothing else, and do end-to-end learnable. So now I contradict myself because now I'm going to talk about end-to-end learnable stuff. And it also has the same desirable property as the lexicalization-based models because it can generalize to unseen slot values as well. And yeah, so the main idea is, I think you'll see this figure quite a lot in the talk, is to use the power of representation learning, meaning word embeddings, with some of the ideas that were also present in the lexicalization-based models. And okay, so I don't know if, do I have a laser pointer here? Okay, yeah, this one. Okay, so the main idea is to actually get the list of slot value pairs from your ontology, and then to, instead of doing like a multi-way classification, multi-class classification, you actually, for each single slot value pair, you have to do a binary decision for the current user utterance, which will detect whether this slot value pair was expressed in the user utterance or not. So basically, your output is always are ones and zeros here. And it is much easier to compose it that way. And so that's one trick here. Another trick is to use representation learning to actually learn like a summary of the user utterance just based on word vectors, and then to combine this somehow with candidate representation for each slot value pair to see if this was actually expressed in the current user utterance. That goes through this semantic decoding module. At the same time, we need the context of the dialogue, and the context is provided by the previous system act. Because we'll get to that, but so system can ask, would you like Indian food? And then actually the gist of information is actually coded in the system act, not in the user act, because then the user can just say yes. And if we have yes out of context, it doesn't mean anything. And that's why we have to keep the previous system act and build context representation from the system act, and then combine context and semantic decoding, which is actually the combination of user utterances that we check whether the candidate pairs were expressed in the semantic decoding module into the final binary decision-making module. And so first going to user utterance representation. So the very first idea that we had is just do like a deep neural network model, which is basically just summing over unigrams, bigrams, and trigrams. So it's quite simple. So you just for bigram or trigram, you just compute the representation of the bigram and trigram as the average over unigram embeddings that you detect, and then you just sum over all unigrams, bigrams, and trigrams, and then you have some nonlinearity appended on that, and the final representation of the user utterance is like a summary of all these unigrams, bigrams, and trigrams that were fed into the nonlinearity here, and that's it. So a very, very simple, straightforward model. And the next one is also like an application of a standard convolutional neural network with, I don't know, I think it was 300 filters. It also works over n-grams up to the length of 3. And then you again have like, relative nonlinearity. It's the most common CNN that you can think of, and you finally average the representations for unigrams, bigrams, and trigrams into the final utterance representations. So it's not important that you understand from start to beginning how this works. It just, the more expressive the encoder for the user utterance, we might actually get to a better model in the end. Okay, so yeah, this is already what I said already. So how do we actually use these learned utterance representations? So user utterance representations, they interact with slot value pairs and their representations through this semantic decoding module. And this is a per turn decision. So we have to detect whether this particular pair was expressed in the current user utterance. And yeah, the idea is basically to just take word vectors of slots and values, each slot and value, and transform them into the representation that has the same dimensionality as the user utterance representations, and then do element-wise vector multiplication, which will give you the information whether these slot value pairs were expressed in the user utterance or not. And for modeling context, something similar is done. So this gating mechanism, I don't remember what that was exactly. Okay, so so I think the idea is that actually it's always the last system act that's most important, and we can actually divide the last system act into two different groups. So the first one is system request, when the system asks something so user actually has to provide this extra information, and the system confirm is where actually all the content is in the system utterance, and the user just says like yes, or like what type of food would you like, and the system just says, and the user just says any. And basically what we do here is, just a second. Oh yeah, so for each slot and value pair, so if we go back here, we actually have to check whether they were expressed in the last system act, and they interact here, and and finally we get the we get this vector which says, okay, it was system request or it was system confirm, and we combine them. So we do the concatenation, and finally we do a classification model that takes into account this vector as well as the vector from semantic decoding. So this one, and combines them into the final binary classification output. Okay, and yeah, another thing that is kind of obscure in this model is, yeah, how do we choose the final intent? How do we actually build the belief state, the actual distribution of all possible dialogue states? And what this model does is something that's kind of handcrafted and ad hoc. And so basically, it just computes values that for each slot value, it gets this probability that this slot value pair was expressed given the last system act and previous probability of that slot value. And then, yeah, this lambda that kind of interpolates between the two was tuned to this particular value. And what the model actually does, it just takes the maximum probability as the current intent. So it doesn't keep the whole probability distribution. So it's not actually a valid distribution. It's just like a discrete set where the system designers just said, okay, if the probability of the highest scoring slot value pair is above 0.5, we're going to take this as the new goal. If it's not, we're going to just stick with the previous goal. And yeah, so it's not so scalable to other domains, and because you always have to handcraft it, and it took quite a lot of time to actually handcraft this, and we'll go back to this point later on. And okay, so now we have to see how our model actually works. And we're going to use two pretty well-known measures from dialogue state tracking. So yeah, the first one is called join goal accuracy, and the second, which actually is the proportion that it gives you the score that all search goal constraints from the user, like area, food, number of people were detected, identified right by the system, and requests is the same thing just for requests. So if, for example, I know address was correctly identified, and the experiments were done on the DSTC 2.0, which is a pretty well-known evaluation data, but we also did more experiments on this Wizard of Oz data set that was compiled in the work of Seung-Shan Wen and Nikola Mrkšić recently. And unlike in DSTC2, Wizard of Oz data set is semantically more variable and flexible because here humans didn't talk to each other, they actually typed. And so they used a more variable language, and it has token to type ratio is actually lower than in DSTC2. We just have like larger vocabularies, more expressive language. So it is harder to model, and this is where actually we expect semantic word vectors to really give us the advantage. And yeah, the results are as you can see here. And so I think baseline DST, that's the Delexicalisation-Based model, and without semantic dictionaries, so just like ordinary keyword spotting without dictionaries. So if you use dictionaries, it goes up quite a lot, and also for DSTC2. But then you can see that we can boost it even more without semantic dictionaries if we just use semantically specialized word vectors. So these results are with semantically specialized word vectors. And so no dictionaries, just general domain embeddings with manual knowledge coded in. And so this figure here also illustrates that standard distributional vectors are not as good in the task. Okay, they do improve a bit over Xavier vectors, and these are actually random vectors where you don't have any semantic information coded in. So you just plug in your random vectors, and okay, the model learns something, so some parameters are learned correctly, but they can't surpass semantically specialized vectors. So these ones were pre-trained vectors from John Wieting. So we even got the better results later on with the Attract-Repel model. And it's funny to see here that like random vectors do even better than distributional vectors for visit the WOZ dataset, which is a pretty weird conclusion. But yeah, this is just what happens because we have so much rubbish still coded in the distributional vectors. We actually have to get sorted out, get like tease apart similarity from relatedness in that. And so, but then this was only English dialogue state tracking. And the funny fact is basically that we still don't have a lot of evaluation data, a lot of training data for other languages, for dialogue systems. And what we did was we collected a similar Visit the WOZ data set. We actually translated it to Italian and German, and then tried to see how well the same modeling technology actually performs in those two languages. And one problem with English is also that it's really simple. So just imagine doing your dialogue system in Russian. You have all these problems with morphology and different inflections and derivation morphology, which are just not present with English because it's such a simple language from those perspectives. And what we actually see here is, okay, specialization still helps. So these are Simlex scores when we do our 4-lingual vector space where all these 4 languages are coded in. And we also see the boost with specialization vectors. So, and cross-lingual seems to help both for Italian and German, but we also see that the results just go down as the morphological complexity of the language goes up. And so, yeah, with German, we do have a problem with data sparsity because of all the compounds and all the morphological variants. And you could imagine what would happen if you start doing your dialogue system in Finnish, for example, or Turkish. But now we have like a new dawn in NLP that's focusing on subword level models and how to enrich word level models with subword level information. And these models, like maybe you've heard of fast text vectors, so they already do better than your ordinary word-to-vec word level distributional vectors on these tasks. And yeah. So one thing that I want to go back now is, so I've talked about cross-lingual word embedding modeling, which gives you shared vector spaces. And so the idea now is, so the first idea is, can we use English training data, which is abundant, to actually boost our dialogue state tracking models for Italian and German? And the answer is yes, yes, we can. And another trick that we did is kind of what we call ontology grounding, which basically means, okay, in the ontology you have all these slot value pairs, which food equals British. So in the other 2 languages, we might actually have like different morphological variants of the word German. But let's just replace all slot value pairs in Italian and German ontology with the one from the morphologically simplest language, which is English. And that's kind of because at a high level, these are all the same concepts. So food equals British doesn't have a language per se. It just expresses this concept. And we did this ontology grounding. And we also did experiments with shared cross-lingual word embeddings where we used different amounts of in-language training data for the target language. So this is the number of dialogues in Italian and in German. And you can see that even if we use 0 German training data, dialogue state tracker still works more or less, not really in a great fashion. Or with Italian, it looks like more decent. So like the number is around 60, but using English training data. So this is without any Italian data. And once you start adding more Italian in-language data, yeah, the numbers go up. But yeah, I think this is just a start, and I think we can do better here. But I think it's pretty interesting to see that we can use data from another language to actually learn a dialogue state tracker in the target language in one way or another. Okay, so this was like the main part of the talk, actually, and the rest is more like recent improvements on the two basic frameworks, which are Specialisation through Attract-Repel and the neural belief tracker. So I don't know if you want to continue or if you have some questions now. I don't know. Maybe it's better if you shoot some questions now because I also got tired speaking, and then I can give this part. It's like 15 more minutes, or I don't know. Or I can just have a drink for 20 seconds and then I'll continue. Yeah, I never did this talk before, and now I realize it might be too much content, so sorry about that. Yeah.
So the question is, the basic idea behind this multi-language transfer of slot value pairs is that you have a lot of data sets for English, and just if you want to solve the same problem in other languages, you just use this data.
Yeah.
Just simple translation of words.
Yeah. So cross-lingual transfer, that's like a hot topic in NLP in general, because people spend a lot of time trying to develop, for example, cross-lingual dependency parsers, because you have three banks in one language, and the problem is that if you just do like machine translation of it doesn't work that well. So this is often like a baseline model that does just simple translation, but
or maybe it's like a suggestion that imagine that you have to develop some dialogue system for, say, German.
Yeah.
But it's much easier for you as a developer because you already have a prototype in English. You have mechanical Turk, and it's much easier to obtain English data. So you're just doing it the same stuff in English, and then you translate slot value pairs and got the result in German. So
So I think from the developer side, I think that's a good way to start. And yeah, just do the translation, because it's much easier to get English data, do the translation. You will get a model that works quite decently, and then try to like optimize it more for the particular language by maybe plugging in certain language-specific information, like do compound splitting, morphology, variation, and all. So I will talk a bit about that, actually. But one thing why this is important is that through word embeddings, we can also like use abundant English data to train this German. So we can also combine data. And so if we plug in German data, for example, that also helps the English dialogue state tracker a bit as well, because we just have more data to train on, and it gives you kind of, the model will generalize well because it will have to adapt to language specificities when dealing with two languages, which will give you like a higher level of abstraction in theory. Yeah.
Okay, thank you.
Does it work? The first question about the word nets, and actually there are quite a few examples of usage of word nets or something like this, and it's a pity because it's a lot of information and it's very rich information. Yeah. And you just mentioned a couple of examples when we can use when we can learn distributed representations that works better for some tasks. And maybe you can advise, give us an advice. How can we also use those word nets? How can we use those scene sets that we have for many of languages? Maybe there are some ways, other ways, not just use them to build embeddings, but maybe somehow else.
Yeah, for example, like the way we used WordNet is actually super primitive. It's just, like pairwise constraints was saying that, I know, cat and feline are synonyms, but we also have like the whole taxonomy. And for example, we don't use like taxonomical hierarchical links, which actually gives you sort of like entailment information. So people actually started using WordNet now to also reason about textual entailment, for example, on the SNLI dataset and multi-NLI dataset. And yeah, WordNet was actually built for that in the first place, and they found it immensely useful for example, for entailment, which is also one of the central problems in language understanding. So that's one way. And with BabelNet, yeah, we have these cross-lingual synsets, which gives you cross-lingual information. And yeah, another way is also, I think BabelNet also gives you like some sort of cross-lingual clusters. So basically you can use some manual clusters which resemble, for example, cross-lingual Brown clusters, which were used for cross-lingual transfer in the past. So I think it's still underexplored, because even what we did here is just like the tip of the iceberg in a sense. And yeah, there's much more to, yeah, because there's like a whole line of research that just invests so much time into building those resources. And I guess that we just have to merge the force.
So what, it seems that all these ontologies, they are much better, and they will give more for the embedding of the whole sentence than for the specific words. Because all these relationships between words can be extracted and featureized from these ontologies.
Yeah, I'm just not sure, because I think, yeah, most of the repositories are still like at the word level, so they don't really have sentences. But okay, now we have all this work that is trying to learn sentence representations, so I guess if you also have knowledge about words, that could help your sentence level reasoning task. So going back to the NLI task, if you know that like dog is an animal, and then like you have a word, a sentence like dog is running in a garden, and then you have a sentence, yeah, animal is in the garden, that kind of gives you like this word level knowledge that can actually solve like a sentence level reasoning problem as well. But yeah, I'm not sure how to directly use this knowledge for sentence level representations. Yeah, so I also have this in the back. So what we did with MBT is, I think this is really like a primitive way of aggregating word representations to sentence representations. And my very last slide is a recent ACL paper from Salesforce that actually did pretty much the same thing. They just have much more powerful encoders for user utterances and for system acts, because yeah, our system act was just take vectors from the system act, and what they did was actually learn an encoder that really learns a better representation. And then when they combined that, they actually got even better performances on Wizard of Oz. And so there's still much room for improvement, yeah, in encoding text, in like doing this for different types of languages. So I might actually do like a short trip to the remaining 20 slides. Oh God. I have some. Yeah, I'm okay. Okay, so now like the last part of the talk was about is about recent improvements that we did on top of these basic frameworks. So the first one is what we call fully statistical NBT, because if you remember from the previous time, is that we still have this like rule-based handcrafted way of extracting user intent. So we didn't have a proper belief state distribution in the final step. And what we actually did here is, okay, well, we can also learn this. So we can actually learn how to do the belief state update in each step. So this is now an integral part of the whole pipeline. So this is, yeah, this gray rectangle here, which combines the current turn extraction for each slot value pair with the previous belief state, and combines it into the current turn belief state update. And this is now proper probability distribution. And the first model that we tried it's just like two matrices, but the problem is that the columns on the matrices were slot specific, so we kind of lose this generalizability to unseen or rare slots. And then the second variant of the model is restricting the values, the scalar values in the matrix, so that we type parameters together during the belief state update for each particular slot, which gives you this generalizability. It's actually a really simple idea, and the paper will be published in 10 days. And the good thing is that it removes the necessity to handcraft this intent extraction with the NBT model, and so it can be it's now fully learned, fully end-to-end, and it still gives slightly better results than what we had previously with the handcrafted ones. Even, yeah, we don't have to now really design a programmatic rule to do that. Another improvement is trying to marry word vectors and morphology, because that came from the problem that we actually saw in Italian and German, because our numbers just went down so rapidly. And so one really simple thing that we actually did is we actually have a lot of implicit supervision in the language, because due to morphology, for example, in Italian, if you have words like rispettosa, rispettoso, rispettosi, so these are all inflections of the same lemma, of the same base word. And they actually, semantically, we could say they actually mean the same thing. And the problem is that some of the variants are actually really rare in the corpus. Some of the variants are more highly frequent, so they actually get better parameters estimated during our distributional training. And these could be treated as some sort of like inflectional synonyms. So the idea is basically to use the Attract-Repel specialization model to bring all these morphological variants of the same base word closer together in the vector space. And we can also apply a similar trick to antonymy relations, because we often have these standard antonymy prefixes that are added to words. Yeah, you have it in Russian as well. And yeah, in Italian, if you add IR to the word rispettoso, you get the word irrispettoso, which is a proper antonym. And then you also want to drag those away in the vector space. So the main idea is basically this constraints extraction that doesn't come from our resource anymore. It just comes from simple implicit morphological rules that could be written by humans in a matter of minutes, or could be actually even learned from the data. And so the idea is basically to apply this attract-repel thing also on morphological inflections and derivational antonyms to learn different neighborhoods. So for example, if you have a word langsam, so this is before specialization, this is after. So these are all like declensions of this word, and they will all get pushed towards the best estimated vector of all the morphological variants here. And this is something I already said. So this is the process that we did with simple morphological rules. So you can actually add these suffixes, possible suffixes to the word, and then you're just going to keep the ones that actually exist in your large vocabulary that gets extracted from my large corpus. So you get these constraints now. And you treat those as synonyms, and you do the same thing with antonyms. So you have this set of standard antonymy prefixes, and yeah, you just remove all the words that are not in your large vocabulary, and you just end up with having this antonymy pair, mature and immature. And you can do it also in Italian and German. And actually, it really took minutes to write all these rules. We just asked, like a German person, could you give me a few rules? And these are non-exhaustive. And it already helps a lot. So for English, it doesn't help. But actually, that's like a positive conclusion, because English is just morphologically poor. And we don't learn any extra knowledge for English this way. But for Italian, for example, so I think the white lines are dialogue state tracking performance. So you can actually see that the numbers really go up. And the same thing goes for German. We actually get like 4 or 5 points in German by doing just this morph fitting trick here. And this was like really a proof of concept experiment where we just wrote down several rules and tried to specialize the vector space, plugged it into the neural belief tracker, and it worked quite well. And yeah, another improvement to the specialization module. So this might have been harder to spot while I was talking about it. Is basically retrofitting and Attract-Repel, they just specialize words that actually did occur in the external resources. So they don't touch upon any other words. And the problem is actually with long tail phenomena, with large vocabularies, it actually happens that only like 10 to 15% at most of the entire vocabulary are words that actually are present in those constraints, no matter how large our repositories are. And so the idea is, yeah, but we have some useful knowledge coded in the vector space now after specialization. Could we actually learn like a global function that will fine-tune, that will actually specialize vectors of all vocabulary words based on the words that were already specialized, and we treat them as some sort of training examples. So this is the general idea. So we got a proof of concept model published recently. So the idea is, okay, you plug in your linguistic constraints from WordNet or BabelNet, and then you specialize your space by fine-tuning only words that were seen in the constraints, and then you take their original distributional vectors, you take the specialized vectors, and you actually treat those pairs as training examples because you know how the vectors look like before the process and after the process. And then like you learn this black box C deep neural network, which learns how to perturb, how to fine-tune your distributional vectors into your specialized vectors based on your seen words, and then you apply this mapping to the entire vocabulary, to all the unseen words, and you actually get, so this is what lives in the black box. So that was the first work. Yeah, this is like a deep feed-forward network, which pretty much learns like, it learns a regression from one vector space to another vector space. And there was a proof of concept model, and the results, so these are only Simlex results here, and you can see that actually it boosts the performance. The reason why the boost is not so great here is basically because Simlex has only highly frequent words. So most of the words are really seen in the constraints. But if you move to a real life problem like dialogue, you might actually face the problem that many of the words aren't seen, and we actually got better boosts in dialogue. And this also illustrates here, when you apply Attract-Repel, you see that Simlex scores, and this is another data set similar to Simlex, they don't change. And this basically illustrates, yeah, the model does not actually do anything with the words that are not in the constraints. And so this was the setup where we removed intentionally all the constraints from WordNet that actually contained one of the words that were in Simlex and Simweb. And when we learn the mapping, we can actually see that we can actually boost the scores quite a lot. So this is the same thing. Okay, this is the distributional vectors. This is when we start specializing, and yeah, this is variation. And another interesting thing here is that through this model, to what we call post-specialization, we can do a cross-lingual application where by using English constraints, we can learn a mapping function on English seen words, and then we can use this mapping function on our Italian or German vectors because those vectors actually live in the same space. So you can actually learn the specialization of your target language space without actually having a lexical resource in that particular language, which is a pretty interesting thing. So you don't need, I know, Finnish WordNet if you have an English-Finnish shared vector space. And we did some experiments and actually also boost like semantic similarity and dialogue state tracking in target languages without actually having a lexical resource in that target language. And these are some results with, I think it was some GLOB vectors, I don't remember anymore. But yeah, the message is, okay, if we specialize, we improve over distributional, but if we properly post-specialize for the full vocabulary, we get even better. And finally, this is more like a slide. You don't have to understand how the model works. I just wanted to emphasize that we can further improve these models by, as I said before, by learning better encoding functions for user utterances and system representations. So because we just use the simple deep neural networks and convolutional neural nets, but yeah, we can be more clever and use like models with intention, and then the results go even more up on the standard data sets. And I guess that's all now.
I'm just looking for spasibo.
Oh!
Okay. one question
Yeah.
about the other tasks. So you showed us that it works well on some tasks that related to synonymy.
Yeah.
And it works well also for something like dialogue writing.
Yeah.
And what about other tasks that are used to compare some methods of learning embeddings of the words? Maybe any other, maybe you have some clues where it would work better than some other embeddings.
Yeah. So I think one of the messages that I didn't convey well is basically that this specialization is more like a second pre-training step, if you want, because we need different properties emphasized for different applications. So if you want to do something that's more like syntax driven, like parsing or something, then maybe you want to emphasize like some syntax in those word embeddings, or at least like emphasize so if you do fast text versus, for example, skipgram, you will do better in parsing for Finnish and Turkish. We actually tried that. If you want to do textual entailment and reasoning, you might actually want to emphasize hypernymy relation in the space. If you want to do like just some document classification, then like topical relationship is more than enough. So you might actually get well with distributional vectors, or you might actually plug some word association data, and it will actually emphasize topical relatedness and not so much similarity. If you want to do for similarity, this also helps lexical simplification, because there also you have to replace your candidate words with proper, simpler synonyms. So if you have a word like car, you don't want to replace the word car with driver, no matter how related they are. So you want to actually have a word like pilot or something like that. So mostly language understanding wants a similarity, textual entailment wants lexical entailment, hyponymy. So it's more like, you could see it as like one big layer of just distributional learning, and a pre-training layer. Second pre-training layer is specialization towards a subgroup of applications, and then applying better vectors to the subgroups of applications here. And so for example, like neural machine translation, I think this could also benefit from really cross-lingually specialized vectors, because if you want to use cross-lingual word embeddings and extra parameters in neural machine translation, then you also don't want relatedness to appear. You just want a proper translation to be generated on your target side. And I guess, well, interestingly, people haven't really, like state-of-the-art machine translation systems do not really use word embeddings these days, but now people have started thinking about it. And now you have like a burst of research that tries to plug in word embeddings as a like extra piece of information inside it. Mostly like dictionaries for statistical machine translation in 1997 or something like that.
Are there any other questions?
Thank you for the talk. And now I have questions. A question about imagine situation when you ask a chatbot asks about price, and I answer that I want not expensive food.
Yeah.
How you manage this situation, or you?
Oh yeah, that's a good question. That's what we actually work on at PolyAI at the moment, because most of the systems now, they're still very, very rudimentary. So they can't even handle conjunctions. They don't handle negation well. And basically, the idea that we have in the company is, I can't talk about it because it's IP issues, I guess. But it's basically, learning classifiers also for relations, because you can have different relations like negation, affirmation, and things like that. So, but this is not handled in current system. And the data is not even written like that. So training data doesn't have those examples. So we just pretend that we don't face those problems, although in the real world, actually, we do have a lot of those. So if you start talking to the real users, then you actually see that all hell just breaks loose, and that's it. Yeah.
Okay, I will ask mine. Maybe people will think of something else. My question is actually not related to the main topic of your talk. I was just wondering, you have reported the results on that Simlex corpus.
Yeah.
where you reach the almost human performance of like 0.7 correlation. I was wondering if you have done any manual analysis of what humans do correctly, which pairs do humans identify correctly, and which pairs do the word embeddings identify correctly? Are there many many things that humans cannot do and the embeddings can?
But I wouldn't say that like humans can't do something.
No, I mean
because it's more like the gut feeling as a native speaker. They think that this word pair has a similarity score of, I don't know, but yeah, some people might actually have a different opinion about some. So I don't know if anybody did an analysis like that, and because it's a bit harder to do it because we do like Spearman's correlation, and no, I'm not aware of. Actually, I don't know any examples right now to throw in.
Okay, thank you. Any more questions?
Are you working only with task-oriented dialogue, or you are also doing something for question answering, like style and chit-chat and any other types of conversational systems?
Yeah, in PolyAI, we are currently working on task-based mostly because I think we are really like strong defenders of that paradigm, and like in the company we just don't have this freedom to explore chit-chats because they would lead us nowhere mostly. And yeah, so I think the main expertise in the company is on the side of task-based, but that's kind of like a different paradigm, more like you can think of it as like Cambridge versus Montreal paradigm. I don't know if you listen to Julian talking, he was more about end-to-end chit-chat. Yeah, and I don't know, like I think we spend a lot of time just debating about that. And
in terms of the task-oriented dialogue, so usually, are you thinking about how you will combine different tasks into more complex assistants? So when certainly if you look further, so usually you have agents not only for the some narrow task, but maybe combination of different tasks. So what do you think about this? How to manage this?
No, but I mean like, okay, I can't fully talk about that because of the company issues, but we have some ideas, but like, I mean, doing multitask-based conversational agents should be possible, where you just have an agent that can do 10 tasks equal well. It just needs the data, right? And it might be possible to actually train that system so that you reuse some training data from one domain into another if they are reasonably similar. So if you want to do restaurant search and booking, that might be quite similar to hotel search and booking. So then one open question is, yeah, how to reuse some of the hotel data to train our restaurant system, and etc. But I think my personal opinion is more like Alexa skills adding, where you can just, yeah, if you need another domain, just try to get the data for that domain, because I think, yeah, the trick is in the data. You just need in-domain data. Yeah, we can just play research and try to do like all these domain adaptation things and transfers, but at the end of the day, if we get the right data and the right amount of data, I think we can excel at a specific task.
Any more questions, guys? Okay, I guess we're done. And if you have any more questions to the speaker, I think he'll be around for a couple of minutes, so you can ask some more questions if you are shy. And now let's thank our speaker.